Okay, good morning, everyone, and thanks for the invitation. And it's a great pleasure to be here today. Looking at the program, I thought, okay, I will share with you a bit more of what I initially thought to present today, just to give you a flavor of what we're doing and how we can maybe connect later in things that I have seen in the program that are very relevant to us as well. So as mentioned before, I'm based in Oxford. We have been there since 2018. Our group is very much interested in understanding chemical reactivity, and with that, hopefully, contribute to molecular design. So very much interested in reactivity, how bonds break and form. And we go from very simple, a small system, which is often my training has been physical organic chemistry, to understand experimental data and to kind of combine different tools to solve a given puzzle. But also, during the years, we have been moving into supramolecular systems and also enzymes. In all cases, trying to understand the chemistry that can happen inside those containers or inside enzymes. So it's very important. A starting point for us is to have the uncatalyzed, these reference reactions that just tell us how the chemistry, fundamental chemistry is taking place. And then we try to understand how solvent, a container, an enzyme can modify that reactivity. And also, with more data coming in, we have becoming users of the technologies that have been developed to use machine learning models to contribute understanding chemical reactivity and to guide the synthetic efforts in that area. But alongside, and very much kind of forcing to that, we have been developing tools to facilitate our daily work and hopefully to make things easier. So we are not developing the fundamental theory in any case, but trying to contribute with those tools that are hopefully easy to use and are open source to understand chemical reactivity, model solvent effects in solution, and to develop supramolecular cages, just to have a quick starting point for our experimental colleagues and for ourselves to contribute to further efforts. And today I wanted to talk to you about a bit of an aspect of molecular design and how we approach that in our group. We often just use computational chemistry in close collaboration with experimentalists, and the main goal is, can we design molecules that will be biologically active? Okay. How do we do this? We can use a mechanistic approach. So given that we understand something, can we design something new? And for that, we use a range of different tools that I will mention today. And the other approach is to use machine learning. So today, we just want to share with you two examples of how we try to understand chemical reactivity or use data to facilitate those efforts. From the mechanistic side, this is work that has been done by the people in the group here. Some of them have already left, but it's something that we started in 2018, when at that time we wanted to automate reaction pathway, and very related to the talk that has been presented today in the morning, where we used to do just manual work and use chemical intuition, which is still extremely important, especially for challenging systems. But in many cases, we can automate quite a lot of the things there. And at that time when we started, there was something under a paywall that could do transition state search, but without sampling, and then without solvation. So we're interested to see how we could automate the process to go into organic, but also organometallic systems. And this is very important to give you a background for people coming into machine learning. Machine learning is very new for us as chemists, and we have been used to use these methodologies that I'm presenting here. If you look back into 2000, around even 2010, when I was doing my PhD, the things that I was reading were often MP2 calculations in small molecules, maybe some more advanced MP2 single point, but most of the time still people was using either B3LEAP or Hartree-Fock calculations for optimization. And if you look back at what we can do today, is quite impressive. So we tend to focus a lot in the ML side, all the developments, but what has been achieved from the electronic structure methods is also very impressive. We can do full CI calculations today beyond the diatomic molecules. Couple cluster is used. I mean, in most of the papers, you will see that as a standard single point approach, and MP2 has become an easy reference to use with more than 20 heavy atoms, which was impossible 10 years ago. with DFT, we have a long range of accuracies, and I mention here accuracy because that will become very important on what I will be discussing later, on how we use the machine learning models to base on these methodologies. So actually, machine learning, as we use today, tend to still depend a lot on how we can improve in this area. But still, we have challenges. So if we use standard DFT calculations, as was mentioned before, also solvent is a challenge. Introducing entropy calculations is very difficult. And automating things is difficult, but actually has become much easier recently, which is great. But there are still some challenges that we have to face as computational chemists. Personally, we want to do, this is our accuracy range. Imagine that we want to predict selectivity, which is a range of 3 kilocalories per mole. So having something that is around 1 is okay. More than 2 kilocalories per mole error starts to be quite tricky if you are aiming to consider selectivity. So this is more or less the background where we started. And the aspect that we wanted to solve in particular was the automation aspect, how we can make things easier to identify transition state. And there has been indeed very many approaches on that, starting from 2000. I don't have the summary slide here, but it was quite depressing at that time where we started, that there were many tools being developed in the 80s and 2000 and were just not available out there. So hopefully those things have been changing today because you feel that you are reinventing the wheel. And in many cases, the methodologies that we are developing today, us and other people, built on the knowledge of work that has been done in the 2000s, where people started to use computers to identify the transition state beyond chemical intuition. So there have been approaches to identify transition state called single-ended. Either you have a starting point and you propagate your simulation, or you have a knowledge of the two ending points, reactant and products. Maybe you have too many potential products, but you have a knowledge of that. So the aim is to ask the computer to identify a point that can connect the reactant and transition state. So what was developed out there at that point was something that will use 3D representations, but we wanted to start from a 1D representation, use graph as our approach to map the reactants and products, and to consider sampling not only at the reactant state, but also at the transition state. So this is how Tom started to develop this in 2018 as part of his PhD. And the philosophy behind AutoDE is a graph-based approach. So imagine that you have your ChemDraw there. You can save them in a SMILE representation. From that, we can generate a graph representation, and we start to count the number of bonds that we have in the reactant and the product. In principle, we can start breaking everything, all the bonds that we see there, but it's quite expensive if you go to larger system. But if you start to count the number of bonds, you can identify, for this example, that hydrogens, CH bond, they don't change. So there is no point of wasting time on that. But there is a carbon-carbon and a carbon-oxygen that changes. So we start to focus on all the graph representation that will give us this mapping. And there are many of them, but this takes a few seconds. So this is done with network X and takes a few seconds or less than that. And then we can identify the one that is isomorphic to the product. And that is our first starting point to decide this will be our guess representation to start to do geometry optimization and so on. So for example, for this natural product that I'm showing here, actually it took us quite a lot of manual work to do the transition state, and this takes less than 8 hours to just put the SMILE representations and identify them. Of course, you have two different products, so you have to run two different pathways, but that is a part where you can combine automation with your knowledge. So if you think that some pathways are possible, drawing them in the ChemDraw is very easy, and then you can start to do the calculations in parallel. And in this case, we identified, just starting from SMILE, that in this case, the lowest energy pathway is due to this intramolecular hydrogen bond interaction to the carbonyl group. But still, there are many challenges. So we solved this aspect of doing DFT more efficiently, but it's difficult to consider solvent effects. Where do we place water molecules? How do we do sampling? And what do we do with transition states, with transition metals? And in the aspect of solvent, become even more important when you think about DFT calculations. The convergence of that wave function will take ages if it was already taking quite a lot of time. So ways that people try to solve that is using ab initio MD. It's very powerful. You propagate Newton's equations on time, but every time you have to solve the Schrodinger equation, okay? Which means that often you will see ab initio MD calculations done with GGA functionals or cheaper kind of DFT approaches. For many years, I was working on reactive force field, which are great once you have parameterized them. But getting that to that point is really an art. So we're still at the point that people claim that they are super efficient, but they don't tell you how long that takes to reach that. So at that point, this was also around 2018, 19. You may all know Gabor Trani here in Cambridge. He is super optimistic, and I mentioned to him that we want to model solvent effects in this system, and he say, MLPs are the solution. They will solve your life, and then we started trying. They were not as easy to use as we expected. Did require a lot of work, but we are getting there. And I think that I do share the optimism that they are a very promising approach to solve the gap challenge that we have between classical force fields and DFT calculations. And I think that even though they are more expensive than people is reaching the point that are becoming closer to classical force fields and can indeed become even more accurate than DFT if we use better training sets. So just a general summary of what a machine learning potential is for those that are less familiar. If you are familiar with force fields, you know that every time that you want to parameterize a bond, for example, you will need to fit that to a harmonic term. And it's quite impressive that you can describe so much chemistry just using two terms. So you have the equilibrium distance and the force constant. And with that, you can describe bonds, chemical bonds at equilibrium, but also around some distorted areas. But you cannot break bonds because, there is you see the functional form goes up. With the MLPs, you can provide the system with some data, and you can do a fitting and be very much free on the type of fitting that you use. The first initial fitting, if you provide a small amount of data, maybe it's not great. It can describe the equilibrium distance, but not much outside that region. But the good thing is if you introduce active learning, meaning that you train the model, check, and add new data, you can start to systematically improve the quality of your potential. Of course, one has to be careful to not overfit, but in principle, you can have a potential that describes the equilibrium region, but also the dissociating region. And what we do in this case, as we do when we solve the Schrodinger equation, is that we have coordinates. We transform our system into representations. In DFT, usually we use basis set. In this case, we use a related type of functions, and then we use the regression task. So we remove the Schrodinger equation completely, and we tell this black box, give me energies and forces, provided the coordinates. And we have been using a range of different approaches, such as GAP, so kernel-based, but also neural network-based approaches. But what happens when we go into reactivity? The chemical space is much, much bigger. And if you think the amount of training data that is needed, things have been getting better. So the first reported example of using MLPs for chemical reactivity came from Marcus Müller in Basel, and he used 300,000 configurations coming from ab initio data, which is extremely expensive. And this was a gas phase reaction. So if you spend such amount of time of computer, there is not much you can do after that. You train the model, and that is all. But if you see what has been going on in the field is that with active learning, people have decreased from 300,000 to 30,000. And now there are different approaches that have become available from ANI and others, but still they use more than 10 and 20,000 of configurations for a specific chemistry there. Some others, we could not even count the number of configurations that were needed. So for us, what was very interesting is that we don't want to develop a super general approach. We want to make the training much more efficient for the chemistry that we want to look at. So that was the aim, looking at how people was doing training, how we can speed up that process. And this is a work that also Tom and Tristan started, and now it's continued by Han Wen and Veronica. And this slide summarizes the workflow that we use, but has been small contributions from different people in the group trying to use the frameworks that other people have developed, which we're extremely grateful. Some of them have been developed here in Cambridge, as you can see, and combine that with knowledge that we have from developing AutoDE, for example, how important it is to use different packages because they have different functions available. So we have combined this to that. So we can generate training data and generate the potential and use that at the same time. More recently, we have introduced other approaches for active learning. So we use enhanced sampling to optimize that process. And then to run molecular dynamics using ASC, but also OpenMM and other different tools. So how do we do the training in that case? So imagine that we want to look at a reaction in solution. Rather than running just ab initio MD simulation, we compute the transition state using AutoDE, just in gas phase. Maybe we'll use implicit solvent if the chemistry requires so. And then we do some random displacement. So our first training will be maybe 10 representations, and that is all. The train model will not be great, but we can improve with active learning until we enhance the accuracy. If we have solvent, we can also train solvent independently and then combine the knowledge of these two training sets into a train potential. And so far, we have been using, and people that have been using during active learning is energy. So we compare the energy between the reference ground's true value and the one that we obtain. And based on that, we use to select new configurations. If the energy is too close, we remove that. But also if it's too far and not relevant to the chemistry that we are exploring, we also remove that configuration. And with that, we were able to train models even at a higher level of theory than DFT. Because once you train, and this is often the approach that we use, a cheap approach but reliable. For example, PV, we know that energies are not great. It's tend to underestimate energies, but we know that geometries are very robust. So we can treat at a PV level. Once we have a stable potential, we can enhance that potential, we call uplift, at the coupled cluster level. And then your potential can reach coupled cluster level of theory. Okay? We have used these for methodologies that where DFT, static DFT, will not work. For example, in this reaction, you have a trifurcated pathway where you have one transition state going to 3 different products. And it's just the dynamic effects that are determining the product that is formed, in this case, the middle one. And what we see here is something that has been mentioned before, but it's important to remember. We try GAP and other different approaches for this methodology, different hyperparameters, and the main difference indeed was having different ground truth values. So you can see that in most cases, the red one is the major one. You see a lot of green. That means going just back to the reactant. But in some other cases, if you use PV, you get the other product. So the preferred one in this case will be the blue one. And from that, you can just see that if you use a different ground truth value, you will get different results. And we still spend quite a lot of time benchmarking. We know actually that this methodology is great for geometries, but energies coming from that, especially for chemical reactivity, are not good. And our benchmark was indeed favoring the use of this functional. So it's just a reminder that the quality of our potential will really depend on the quality of the ground truth value. And with that, we have been moving into how we can even make the training more efficient. Maybe moving away from the energy descriptor into other descriptor. Do we need to compute energy every time that we have new configurations to check if they will be introduced in our training or not? So we have removed this by using similarity descriptor. Just based on geometry, can we determine if the configuration that is new is relevant for our training? This is just a toy model. This is water, and we're mapping here the different points that we obtain from the training using energy, similarity, and distance descriptor. So in gray is all the data combined, and the color code is indicating which one comes from energy descriptor, which one from the similarity, and which one from distance. And you can see that the number of points that we require to reach the same accuracy of the potential is reduced significantly when we use similarity and distance. Okay? Energy descriptors tend to map very close to the energy, to the minima. So it's difficult to escape the minima. And we have seen that actually with this type of descriptors, similarity and distance, we need fewer number of configurations, and we can actually explore the energy range, the chemical space much more smoothly. While with energy, we tend to be located in the low energy regions. So it's more difficult for the system to escape and populate other regions. And using those approaches, so moving away from ab initio MD, using cluster models where we start to understand the intrinsic chemistry first in gas phase and slowly training increasingly complex models, and then combine them later. And using the distance and similarity descriptor, we have been able to do chemical reactivity in full explicit solvent. This is just for a Diels-Alder reaction, where we can see that actually the influence is solvents. What it's doing is doing the reaction much more asynchronous. So we can now run hundreds of simulations downhill from this strain potential, going into reactant, but also into products. And we see that the product is concerted, but it's very, very asynchronous. So you have a very short life intermediate, just a few femtoseconds being formed there. That is not observed if you have implicit solvation. So the synchronicity of the reaction changes, and with that, the energy barrier is all reduced. So now we are very much focusing on introducing enhanced sampling. That is, again, to facilitate the training that we do. And as a toy model, we're using this SN2 reaction. So imagine that you don't know the transition state. So we often start from the transition state downhill. This is the approach here. But at some point, a referee said, but what happens if you don't know the transition state? You should try to start from downhill, from uphill dynamics, which we have done, but also maybe try other ways to enhance the sampling. And this is what we have been introducing more recently with metadynamics. Okay? So if you see, we go from different iterations, 1, 2, until the very final one. And we start to populate the chemical space related to this simple reaction. And what you can see that is with metadynamics, again, we can sample much more smoothly the energy range. Okay? So sometimes we require more configurations, but then our potentials tend to be more stable than the one that we obtain through downhill dynamics, because we are sampling the chemical space, and you can see here in the energy range. So we start here, but slowly we start to move around until we populate the reactant and product side. So both approaches are valid, but the well-tempered metadynamic allow you to explore with much more freedom the chemical space during the training process. So rather than doing that after, you do that during training. And this is more or less the summary of the first half of the presentation that is very much based on how we can improve our understanding of chemical reactivity, and from there, hopefully, contribute in the molecular design effort. It's a much more fundamental approach that we go one by one, and I will say, when we do this type of simulations, we are not aiming to do high throughput modeling. It's very much trying to understand the mechanism, the fundamental chemistry that is taking place there before going into the science efforts. And just a few take-home messages is that using locality, meaning cluster models, and rather than doing full ab initio MD, is working very well. We can reproduce macroscopic properties from these training sets, and introducing selectors that are much more efficient has been key to have training sets and train models in a day or two. We have been able to introduce in that way solvent models in a way that we can describe the chemistry and the solvent at the same time. And now, more recently, we have been introducing enhanced sampling, which is very important when we want to go into more complex systems, which we don't have knowledge of the transition state. And the other aspect that I wanted to talk to you, the second point, is what happens if we have a lot of data, which means that doing this type of very detailed simulation doesn't work, it's too expensive. And this is the work that we have been doing in the area of heterocyclic compounds, We were very naive initially. We wanted to do this modeling, doing a lot of transition state and identifying activation energies and for them selection, but we realized it was too expensive. Why do we care about those models? Well, heterocyclic compounds, for those working in medchem, are super important. Always there is a patent behind each of them, so people want to discover completely new, patent-free scaffolds. They are present in natural products, so in principle they are very promising for medicinal chemistry, but many of them have not been explored synthetically. And they can improve chemical properties, especially polarity, lipophilicity, in a way that is impressive. One single chain can make significant difference in the drugs. And there was this study when we started to work in this project a few years ago, the vehicle data set, that tried to identify with a few rules all the potential heterocyclic compounds that we could have with 5 and 6 member rings. Okay? And with a few rules said most of them actually are just crazy, cannot be synthesized, but there are a few that are present and a significant number, a few thousand, that have not been synthesized, but in principle could be achieved. And since then, only a handful of them has been synthesized, so we were thinking, what is going on? Can we see if anything can be obtained from those that are maybe possible, but have not been reported yet? So in that case, we have more than 3,000 compounds that can be synthesized. So let's think how we can obtain them. And our initial approach was to do retrosynthesis using the tools that were available 3 years ago. At that time, the IBM reactions data set was just coming out. So we thought, okay, we'll use them. Retrosynthesis is challenging for chemists, even though Goodward put that in very nice words. If you talk to synthetic chemists, they will not see that as a poetic description of the approach. It seems very logical, but actually it's a lot of brute force and hours of work in the lab. And the idea is that you start to break down your molecule, target molecule, into small, simpler or equal complexity sub-targets until you reach something that you can buy easily. And again, as with machine learning, this is a field that there have been many, many contributions in the area of organic chemistry, and more recently from the computer science side. And I will just mention the approaches that most of them have been based in template-based approaches, like the AstraZeneca ScienceFounder approach, where you try to, based on the knowledge that you have of the chemistry, the bonds that are broken and formed, can we learn something to generate new molecules? And around 2019 to 20, there was a work coming from IBM in using a transformer, where you don't have any template, it's template-free, and you start to make predictions about the product or the reactant that you have based on the information that you give. So in this case, you can have a product and get back a reactant using a translation-based approach. So our aim at that point was, let's use this technology that is just out and working very well. But what we realized that using the tools that we have there, in many cases, we didn't have meaningful disconnection. Either there was not solved in many cases, was giving us no answer at all, or some of the disconnection were very trivial. They were A protection, C protection, not even touching the ring. So I didn't know that a ring could be broken. Thinking about that, we thought, okay, can we do something? And that did make sense. If you see the data set that is used for training, mostly is the USPTO data set that is used. Only 5% of them correspond to ring forming reactions. So we thought, can we use this knowledge, have the models that are out there, and introduce the knowledge that we need? So introduce knowledge from the ring chemistry, and this was 160,000. Many of them were coming from manually curated data from EVA, but others coming from the Pistachio data set. And what is important to highlight is that the heterocyclic compound space is very large. So it's not like doing retrosynthesis for one type of chemistry. You have amide bond formation, you have condensation, you have different type of chemistry, and you see here in the chemical space. So this is the general chemical space of the training set that we're using, and this is where in blue our added, the curated data set is coming. So it's populating different areas of chemical space. So this is what we did. We started to, sadly we have to train again. The models that were out there because in many cases data is not available. So we did the curation and we did train our own general model and then improve that into a ring data set. That is very much, as we say, it's like trying to consider the knowledge that you have as an undergrad, maybe adding that with a bit of knowledge that you have as a PhD student and trying to make the most of that. Sometimes as a PhD student, you have a lot of specific knowledge, but you are not able to do simple chemistry or the other way around. So can we mix them in a different way? And there have been ways to mix that. So we started to test the different approaches. We tested a few, but the main ones that I will be presenting today is the fine-tuning, developed, introduced by IBM, and the mixed fine-tuning. And the difference is how we start to teach the model, how much data you're given about the specific chemistry and the general chemistry. Either you give general chemistry knowledge and later add the specific knowledge. This will be like going from undergrad to PhD and to do a project. This is known to work very well for the specific chemistry, but tend to forget the general easy chemistry. What you can do also is train both of them in parallel, which often tend to forget this small side data set, but later add a combined baseline model. So you try to teach both things, but also try to remind the model of what is the baseline general chemistry data set. And we compare them to the ring breaker approach developed by AstraZeneca, which we again retrain a bit to be able to make comparisons. How do we evaluate performance? This is something that people is being much more careful these days because it's difficult to compare. Everyone uses their own metrics. The one that are popularly used is top-end accuracy, which means can your model predict? Often we have 5 predictions, 10. You can ask your model as many predictions as you want. Can you compare that one to the original one? People tended to compare top 1, but top 1 is just memorizing. It's like, can I repeat what I know before? And people tend to use now top 5 or 10, giving more freedom the system to suggest new chemistry. So even if that doesn't match the ground truth value, maybe that is still relevant and useful. But also trying to check this through a forward prediction. So if you predict this, can the model go back and predict the final product, which is giving you the round true accuracy introduced by Theo Laino and Philip Scholler. So we're trying to use the similar metrics. So how did we do in those approaches? So for heterocyclic formations, you can see that our baseline model, based on the transformer approach, is here. And I'm presenting kind of the more challenging data that is doing retrosynthesis. Doing forward is very easy, and you can get 200 very, very easily here. Our model is improving. It's not significant, but you can see that the model is introducing several thousand of new predictions that were not possible. And more importantly, this baseline tend to present chemistry that is not ring breaking. So we are ensuring that all the ones that we have here are ring breaking models. How do we do in the general chemistry knowledge? The fine-tune model, as expected, is not doing great. This baseline is doing perfectly fine for general chemistry because it was trained for that. And the mixed fine-tune is the one that we have chosen. We are continue working on that because we think that is the best balance between improving accuracy for the heterocyclic ring formation and keeping the chemistry that is well known. Something that I mentioned, as I said, the baseline can solve many points, as you saw, around 40% of them or more. The problem is that if you look very closely at those predictions, the baseline tend to do this. It's just doing some deprotections there. While with the mixed fine-tune, we can have true chemistry forming bonds. So we can have a click reaction, we can have a condensation reaction, which in many cases, the reduction of complexity is not seen by the baseline model. Yeah. So in all these cases, it's just a few examples how we can improve. So this improvement that seems small is significant in the sense that we are now targeting the ring closing step. How we can do compared to the template base. Actually, template base was developed specifically for heterocyclic compounds. Okay? And what we can see here that, again, if we use these metrics, we can see that in many cases, we can do better than the template base. Especially, we can solve many things that were not able to be solved there. We have to say in this case that our training set is a bit more diverse because it's newer compared to the original one. So we are giving the model more information than the original template base. And where we are at this point on this, we really want to combine, because we're doing single-step retrosynthesis, which is great, but often retrosynthesis is not one type of chemistry, it's many different steps. And we have been combining that to RetroStar, which has been developed by others. So we have been using this approach and combine that with the general chemistry knowledge that our model already have. And these are just two examples that we took from 2023, taking data just until 2022 for training and asking the model to predict these two different examples that I will be showing you today from the Journal of Medicinal Chemistry. So in this case, this is a relevant molecule that was synthesized there, and we can see that we can reproduce the literature data very well, while the baseline model that we have for this retrosynthesis process just didn't give us any results. In another example, we can see that both the baseline and the mixed fine-tune model are giving us these connections, but only our model is giving the disconnection that allow you to break the pyrazole bond here. Okay? And we are using, in many cases, both approaches, the baseline and the mixed fine-tune, to see if we can discover different chemistry. Indeed, we have seen that sometimes the template-based model works better for some chemistry. Sometimes it's our mixed fine-tune based on the transformer. And we very much want to combine them and be very agnostic. Which one can give us the best approach? And if we see the same results, maybe this is encouraging to support that given synthesis. So where we are now in this one, we move away in this case from doing this very detailed mechanistic analysis because the chemical space was huge. We have 3,000 potentials heterocyclic that we wanted to synthesize. Mechanistic analysis with transition state search was just a crazy approach to consider. And this has been giving us some insights, which we are now targeting a few heterocyclic that we think are promising and interesting to synthesize, and exploring the chemical reactivity of those. They have not been easy to synthesize or characterize, but for those one, we can do more fundamental chemistry there. Okay. And with the retrosynthesis approach, we have been very much kind of newcomers to the field. Using approaches that have been developed, we have seen that the mixed fine-tuning for us has been the best approach. And we're very excited to be using that for multi-step retrosynthesis before doing any mechanistic analysis, which we still consider extremely important. And with that, I would like just to thank the people in the group that has been doing all this work, and particularly Eva, who has been leading the work in retrosynthesis, and Veronica and Han Wen, who has been leading the work on machine learning potentials, aiming to introduce solvent effects in chemical reactivity. And to all of you for your attention. Thank you.